is the collaboration of many people. Kitagawa, Ono, Hayashi, and H. Yamaguchi is a very, we remember his name very well, and Professor Tanabe. Unfortunately, Mr. Kitagawa is not available today, so instead, Professor Tanabe will make presentation. Okay, please.
So, thank you, Professor Takahashi, for kind instruction. My name is Katsuaki Tanabe, running a small lab in Kyoto with a couple of students. Let's see. Right, and importantly, this time H. Yamaguchi kindly gifted us his old apparatus for experiment, and then we modified and reinstalled the equipment, and then today I'm gonna report our simultaneous detection of excess heat and neutron emission from a palladium plate type samples. So the main feature of our facility is a gas phase chamber with a bulk palladium plate which is loaded with deuterium gas, and then we directly apply bias voltage across the thickness of the palladium sample, and then make a current injection through the plate so that we can stimulate the reaction by Joule heating as well as by electrodiffusion or migration. This way, particularly we cap one side of the plate with gold film as a diffusion barrier to induce a one-sided diffusion of deuterium atoms for the simplicity of our analysis. And this way, in addition to the conventional diffusion induced by pressure gradient or mass concentration gradient and thermal gradient as a driving force, we can induce by the direct current injection a strong atomic movement so that we can induce a probably higher stimulation force because we all know the strong dynamics of the atoms and as well as probably electrons are very important to induce this kind of reaction we are focusing. This is the setup and procedure of our experiment. First, we anneal the palladium sample around at 1,000 degrees to make a monocrystalline phase as well as a decreasing or a cleaning of the surface, because we found that for insufficient condition of the pre-treatment, we cannot obtain a good or reproducible absorption of deuterium. And we deposit gold film for one side of the palladium plate as an electrode as well as a diffusion barrier, as I mentioned in previous slide. And then we loaded deuterium gas into the palladium sample at room temperature and atmospheric pressure. And then Joule heated to stimulate the reaction with a tungsten probe or electrical needle attached to the sample to make a current injection through the sample. And as we investigated the diffusion or desorption of the deuterium out of the palladium plate, we found that even during the 10 or 15 minutes in our deposition procedure, a significant amount of desorption happens for deuterium out of the palladium, so that we changed from the Yamaguchi's procedure to, because he deposited gold film after loading, but we switched the procedure so that we can sustain a sufficient amount of loading inside palladium. And a difficulty of handling Yamaguchi's 20-year-old apparatus is because his apparatus was running in France for an international project led by Imura Europe, and the leader was Stanley Pons at the moment. But after moving the apparatus into my own lab, we found that almost all of the electrical parts as well as mechanically moving parts are all gone. So we need to totally renovate it, as well as a listed here. We added some modification for particularly for higher sensitivity of the action or characteristic of the sample. And then which took almost 1 year and a half to start our experiment, but thanks to a good advices by Yamaguchi, we could nicely start our experiments. And then, so first, I show you the temperature evolution result, and we conducted experiments with and with and without deuterium loading, with almost same amount of applied electrical power onto the sample, and then we see a solid curve, the case with deuterium, and the dotted line without loading, so that we see some difference for the temperature. Although the applied electrical power are almost same, and then we here analyze what our results said. The main feature was the temperature. We have some points of drastic increase in temperature, despite of the decrease in input power, so it may indicate something. And then also importantly, the observed system is a deuterium desorption process, because the temperature of the sample is rising, and then so basically desorption of deuterium happens, and then but the palladium temperature increases. Although basically the gas desorption processes are enthermonic, so the temperature should decrease because of the desorption, but our experiment says it's the temperature is increasing. And then we didn't observe such a rapid increase or acceleration of temperature in the reference control runs without deuterium loading. And even when the input power was smaller for the run with deuterium loading, so the main runs of experiment, than that for the control runs without deuterium. So and the temperature attained with deuterium was even higher, despite of the containing endothermic deuterium desorption processes. So that the temporal behavior of the heat generation is cannot be simply explained by non-chemical or physical chemistry processes, which indicate an existence of some nuclear processes or unknown phenomena. And then we also observed excess heat, as I will show later. And neutron detection. So the purple line is the neutron intensity we detected outside of the chamber. And then we observed signals at timing corresponding to the accelerated temperature points like this. And so we have a anomalous point of temperature increasing. And then at the same time, we detected a strong emission of neutrons. And as we approached or moved our neutron detector closer to the point of the palladium sample, the signal got much higher. And as we estimated, the signal intensity was nearly proportional to the distance of the position of the detector from the sample. So presumably the neutron signal or neutron emission comes indeed from the palladium sample. And then when we extrapolated the emission intensity, considering the spatial three-dimensional 4 pi angle out of the sample, we estimated the intensity was approximately 200 times stronger than the environmental background. And here I will show you some of the previous results. And Professor Jones showed this is the very first experiment and some intensity of neutron. And then Professor Dinino has a very strong detection for neutrons. And then a Japanese group also in the first, in the earlier stage of this field, detected some emission. And then importantly, Mizuno detected a temporary, not coincidence, but the temperature increase a little after the neutron burst. And we know many other reports for the neutron emission, but importantly, there are a few reports that correlate neutron emission and the heat generation temporarily. And our result of the temporary simultaneous generation of neutrons and anomalous heat may be a good indication of some nuclear reaction or phenomena in a solid. And then we estimated the excess heat generation by calibrating the heat capacity and heat transport parameters as shown here. And then we first ran a blank experiment control without deuterium loading, and then defined the parameters for heat conduction, accounting for the radiation as well as convection diffusion transport of heat. And then the fitting result was almost perfect, so we are relatively confident for the calibrated parameter. And then the result is like this red curve. This is excess heat. This is the 0 point, so break even. And then we see a strong or some generation of excess heat, which was around 0.5 watt. And then importantly, the peak of the excess heat temporarily coincides with the generation of neutron signal, so which could be a hint to analyze the reaction mechanism. And we are gonna go for the details in the future. And then we also observed a bend for the plate, which was opposite direction as the Yamaguchi's experiment 20 or 30 years ago, which we don't know the reason though. And then we investigated the curvature in related with the phase changes, beta, alpha phase. And then we found that the curvature was probably a good agreement with the difference of the lattice constant in between the alpha and beta phases, as I will show you later. And then first for the bending observation, we first wanted to exclude very trivial causes potentially. First, the bending might happen due to the thermal expansion or strain due to the temperature increase or profile. And also the strain due to the difference in thermal expansion coefficient between the palladium and the gold film. And also, probably this is a stupid possibility, but simply the plate did not fit in our holder when it expands, so it bent. But as we examined for all of those three, they could be excluded very easily. And on the other hand, the change in the lattice constant, as I mentioned a little bit before, in the phase transition was around as large as 3%. And then from the curvature of the bent sample, we estimated the expansion of relative expansion of 2% around about, although we had some variance for the bent situation, so not quite reproducible. But so probably the bend is related with the phase transition. And then Yamaguchi mentioned that in his case of the bending direction, probably blistering by the tensile strain due to beta to alpha transition at the gold surface, which is the surface of palladium plate, which was not deposited with gold, made it expansive, and then this convex after the wall palladium plate become alpha phase. So such a blister made the bend. That was one possibility, but our situation of the bending direction was opposite. So we don't know we cannot fully explain the result. And then we analyze by using X-ray diffraction. And then main point was each peak split into two during deuterium loading, and the peak positions differ between the gold and non-gold side of the plate. And the one of expansive shift, which is represented by the decrease in the diffraction angle, is attributed to beta phase formation by the deuterium loading. And the other one may be alpha phase, but shrinkage is not understood yet. Probably due to the palladium recrystallization during our experimental runs, but the temperature may not be that high, so we are still wondering. And the peak position difference between the gold and non-gold side indicates a lattice constant variation or distribution, so some profile of the lattice constant exists inside the palladium plate across the thickness of the plate. And therefore, the band is attributed to the spatial lattice constant variation due to alpha beta phase transition. And the band related to the phase transition, we wanted to investigate the strain induced because it bends, so some strain spontaneously inside there. So the atomic distance between the deuterium atoms decrease in palladium atom is possible, and we calculated if it happened under some strain. We used a EAM potential method to calculate the potential two-dimensional potential surface inside our palladium plate. But unfortunately, we didn't have data or parameters for deuterium. So we used the case study hydrogen inside palladium. And this is the result. And in summary, we observed in our simulation a shift of the stable site. So as you know, in the standard condition, octahedral site is the stable. However, it shifts into the tetrahedral T site due to the strain. So in the bending or due to the phase transition induced by the diffusion or desorption of deuterium atom, such shift of the stable sites are possible, so that we may expect some strong dynamics for the movement of electrons as well as deuterium atoms, which may be related with the reaction. So this is a summary of my work, heat generation and neutron generation are simultaneously detected, which may be a key to analyze this field of reaction further. And then we also analyzed by using X-ray diffraction as well as EAM potential method calculation to correlate the atomic movement with the lattice strain. So thank you for your attention.
Thank you, Professor. I think we are happy to see the very renewed experiment of Yamaguchi type gas loading method. So now paper is open for discussion. Larry first.
Yeah, just one quick comment. You've got another diagnostic in there. Your gold foil undergo neutron capture. If these are thermal neutrons or reasonably slow, will go from gold 197 to 198. And that's got a roughly 2.8 day half-life, but it's got a very solid 412 keV gamma line. Oh. You could pick that out with sodium iodide.
All right. You probably...
It's gold.
You mean the decay rate?
No, the gold that you've got on there would act as a neutron witness material. It would activate. And you would see that it's a 412 keV gamma line, and it's got about a 2.7, 2.8 day half-life.
Oh, right, probably.
And it has a reasonably high capture cross-section in Barnes.
Oh, yeah, unfortunately, we haven't detected any gamma rays, but probably our detectors are not very pretty cheap ones, so we are going to renew that to detect, as well as the energy spectrum of the gamma rays as well as neutron is important. So
what I'm saying is you could actually measure this a couple of different ways. The other thing is use a plastic panel which has no resolution.
Oh, right,
okay,
right.
Large area, so you could have that there and close. It would also respond to neutrons, so you don't really care what lights it up. But you could pull the foil after you're done with the experiment. It's got a 2.8 day half-life, and look at it with either sodium iodide or high purity germanium.
All right, all right. Okay, thank you.
Okay, Miley and Peter. Okay,
could you describe the neutron detectors a little more? Do you have any information about the energies of the neutrons?
No, not yet. I think that's probably the first importance to install a spectrum, energy spectrum.
Are the detectors, do you thermalize the neutrons at all, or what type?
Not yet.
And then, what is the repeatability of a neutron emission? Is it reproducible? The neutron emission always comes out.
Oh, yeah. That is pretty reproducible, but I think, okay, so we have run probably like 15 to 20 runs, and around 70% of the runs we detect in neutrons. So not fully reproducible, but relatively still working because every time we change our conditions, so not perfectly reproducible series or experiment, but so we had to first figure out the core condition of the good experimenter, and then gonna make it for the reproducibility, but yeah, I know it's important.
okay, thank you.
When attributing neutrons to a source, it's very important to take into account they might be originating from what's called fractal fusion. Fractal fusion is a way of initiating hot fusion locally in cracks. When something containing deuterium, any material actually, where cracks are formed, local voltages are sufficient to produce very momentary hot fusion, and that's a very big source of neutrons. So you have to be very careful that it is not coming from that source.
Yeah. We also consider that, like you mean the fracture induced maybe acceleration of the direction. Yeah, that is possible. So yeah, thank you.
Not correct with heat. So.
Not yet.
Okay.
One short final question, hooking up with the other gentleman there. Have you been looking at the isotopic ratio of the palladium/gold?
No, not yet. Yeah, we recognize that's important to investigate that.
Right, in relation to the previous question there.
All right.
I could see that there might be isotopic changes in the palladium/gold that are related to the neutron release perhaps. So maybe it's an advisable thing to look at the isotopic ratio of the samples.
All right, yeah, we are going to investigate it.
Thank you.
Yeah, thank you.
Thank you, Professor Tanabe. Thanks again.